In this video, we're going to talk about chiral versus achiral carbons, specifically in cyclical molecules or rings. So let's first review what a chiral or an achiral carbon is. So I'm going to draw an example of an achiral carbon right here, and I will explain what makes it achiral. So notice that we have this central carbon is the one at question. We have a methyl group attached to it. We have a bromine. So far, those groups are all different from one another. They're not the same. However, notice that we have two hydrogens which are identical to one another. And because it has at least two groups attached to it that are identical, it is not going to be a chiral carbon. Another example would be if you have carbon with an SH on it, and then it has hydrogens on the rest of it. The SH is fine because there's only one of it, but the hydrogen is not fine because we have multiple of them attached to the central carbon, and those are all identical to one another, and you just can't have that in a chiral carbon. The next one, just one more example. We have CH2OH, and then we have a chlorine, an amine, and then you could see here that the chlorine is fine because we only have one chlorine, and the NH2 is fine because we only have one of it, but this is not fine, we have two of them, and so this makes it achiral. If you want a carbon to be chiral, then you want all of the groups that are attached to it to be different from one another. And so an example of it would be what I'm drawing on this left side right now. You can see that every different group that I'm going to box in is different from one another. They're not all the same, or at least none of them are the same. That's the criteria. One more example just to finish this off. You can see again all these different groups. We have a methyl, we have a hydrogen, we have an amine group, we have a fluorine. They're all different. So that's the difference between chiral and achiral carbons, in case you need a review on that. So we know how this works on single chain molecules, but on rings it can be a little bit confusing. And I think this is something that you can't find a good explanation for online. Not a lot of people are explaining it well, and I'm going to try and do my best to help you understand this concept. So let's say we have this ring right here. We have a cyclohexane ring with an NH2 on it. And let's specifically focus on this carbon right here. So when you have these bond line structures, carbon's always going to be attached to four things, and even if it's not shown, it's going to have invisible hydrogens. So we're going to have an invisible hydrogen there. We have one there, so we have two here. We don't need to draw all of them, just for the carbon you're looking at, and we're looking at this carbon. So far, you can see that we have an NH2 and we have a hydrogen, so that's fine because they're different from one another. However, what do you do here, right? So what you would do is go for the other group. You can't really box it in because it's not as tangible, but you can just go around like this and draw an arrow. And what I like to do is just do this. I would go, okay, on the right side we go one carbon, on the left side we go one carbon. Everything's the same so far, right? On the right we go one carbon, on the left we go another carbon. Everything's still the same until we meet one another. And you can keep going forever and you still have the same thing for both the blue and the red. So therefore, the two groups that are attached to this middle carbon are going to be the same, and therefore this is going to be an achiral carbon. However, let's change things up a little bit. What if we had an OH on this carbon? Would the carbon we were looking at before, this one, would it still be achiral, or would it be now chiral? So let's do the same thing here. Obviously the NH2 is still fine and the hydrogen is still fine. Those are different from one another. I'm going to go one down on the right side, one on the left. Everything's the same so far, right? One on the right and one on the left, and you can immediately see that we have a difference, right? The carbon I've ended up here on the right side has an OH. The one I've ended up on the left side, it doesn't have an OH, it just has two hydrogens attached to it, which are invisible. So therefore, we can say that the two groups that these are attached to are different, and therefore, if there are no identical groups that this carbon attaches to, then this is going to be a chiral carbon. But let's consider a different scenario here. Let's say that the OH that we were looking at, let's remove it and replace it right here. Now what do we have? Is this carbon going to be chiral or is it not? So once again, let's just go like this. So far is everything the same. One on the right, one on the left, one on the right, one on the left. You could keep doing this forever. You're still going to end up at the same thing on each carbon down, each step down. And you can see on both of them, on the third jump, we've gotten to a carbon with an OH, the same carbon actually. So therefore, we consider these two groups that the carbon's attached to, this one and this one, they're both the same, and since they're identical, it means this carbon has two identical groups, which makes it achiral. So that one's achiral in this case. Now you could take that principle and apply it to a lot of different problems. Let's practice it with this one. So feel free to try this one out. Feel free to pause the video. So I want you to examine the carbon that is on the right side. So this carbon, is that one chiral or achiral? So let's begin by drawing the invisible hydrogen. The reason we have one invisible hydrogen is because without the invisible hydrogen, it has 3 bonds and it needs to get to 4. So far the hydrogen is fine. The chlorine is fine, they're different. Now let's follow, because it's a ring, let's follow the carbons down. So far everything is the same. We have a carbon here, and it seems that on the right side we've hit something different. We've hit a carbon with a bromine, but on the blue side here we haven't hit a carbon with a bromine. We've just hit carbon with 2 invisible hydrogens. So therefore we consider the 2 groups coming out of this carbon to be different from one another, and therefore this would be, since they're different, it would be a chiral carbon. So now let's change up the scenario a little bit again. What if we had this situation? Go ahead and try this one out and see if this carbon would still be chiral or if it would be achiral. So the hydrogen and the chlorine are fine as they were before. We're going to go 1 carbon, everything is the same, and then if you go 2, you can see that everything is still the same. We have a carbon with a bromine and hydrogen. If you go one more, it's still the same. And you can keep doing this forever, and the two groups would be identical. So therefore, we consider the two groups coming out of this carbon that are part of the ring to be identical, and therefore the carbon is going to be achiral. It's not going to be a chiral carbon. So I hope that helps in understanding the chirality of ring structures. Thank you for watching.